All right, so today we are beginning our lesson on conservation of energy. Okay, so here's a quick track for prior knowledge question that you can complete as part of our bell work. A roller coaster is released from point A. Can the roller coaster ever exceed the height at point A? AKA, can the roller coaster ever go higher than the height established by this red line right here? So as mentioned already, our topic for today is conservation of energy. Some announcements. Conservation of energy quiz on Monday. Late work will be due Monday, December 14th. So what we're up to today is, what does it mean for something to be conserved? What happens to energy as the system changes? Can energy be created or destroyed? And then applications of energy conservation in fields of engineering. So if you ever heard the word conservation or conserved before, to conserve something is to keep as close to the same as possible. If we want to conserve a population, or we want to conserve energy, or we're trying to conserve the forest, let's say ecosystem conservation, we're trying to keep as close to the same as possible of that population or the energy when we're exercising, or so on and so forth. So that brings up the main idea behind conservation of energy, which is the idea that, better said, not the idea, but the fact that energy is a set quantity that can never be created or destroyed. So one way that we can consider this is like there's conservation of matter. Matter is a quantity in the universe that we can't create or destroy. Matter is simply converted from one form to another. So like if you burn a piece of wood, the piece of wood is not being destroyed, but rather it's being converted into different forms of matter, aka ash and smoke, and so on and so forth. The same thing is happening with energy, is that energy can't be created or destroyed. It can only be transformed from one form to another or transferred from one place to another place, okay? So energy is simply converted to other forms that we may or may not be able to use, okay? And then when we have energy is converted to a form we can't use, what we say is that there's a non-conservative force that's doing work on our system. This non-conservative force does work that turns energy into a form that we cannot use for our motion. The big thing note is that the energy is not destroyed, okay? So if we take a look at this diagram right here, if we start out at point A, let's say a roller coaster starts out at point A from rest. It has all potential energy, all right? As our roller coaster falls, it speeds up. The force due to gravity speeds up and converts that potential energy to kinetic energy, as we can see right here, all right? At point B, we can see that some of that potential energy has been converted into kinetic energy. Getting tongue-tied over here, okay? However, we can see that regardless of our kinetic and potential energy content, we can see the total mechanical energy, aka the sum of potential and kinetic, remains the same. So there's an inverse relationship between potential and kinetic. As our potential energy decreases, that potential energy is being converted into kinetic energy. The potential energy is not being destroyed, it's just being converted into a different form, okay? Some important things to note is that as our object falls, people tend to think the object is gaining energy because we see it speeding up. But again, the object is not gaining energy. The energy remains the same throughout, this yellow bar, the total mechanical energy. It's just that the energy is being converted from potential energy, which we can't see, to kinetic energy, which we can see. We associate that with the motion of the object, okay? And so as we go throughout the track based on the height of our object, the potential and kinetic energies will change throughout, while the total mechanical energy remain the same. So for example, at point E, we'll have a little bit of an increase in potential energy because we're going up a slight hill right here. We're going to slow down a little bit, meaning some of our kinetic energy is going to be converted to potential as the force due to gravity does work on our object. Now, if this track right here had friction, okay, our total mechanical energy remained the same, except now friction would do work to turn some of the kinetic energy of our cart or potential energy of our cart into heat. So we still have that total mechanical energy remains the same. It's just now that total mechanical energy is being converted into heat between the track and the wheels of the car, which is what results in us not being able to use that energy. So friction would be an example of a non-conservative force. We can't regather that heat and we can't reuse that heat. So that's very similar to how if you've ever seen a car stop or brake, After a car stops or brakes, you may notice the car tires are hotter than their immediate surroundings, and that's because the kinetic energy from the car has been converted to heat due to the brakes doing work on the wheels, causing the car to slow down. Friction between the brakes and the tires converts that kinetic energy of the car into thermal energy, which is why the car tire feels hotter than its immediate surroundings after the car has stopped. And here's just a better close-up of what we've seen right here so far. So here's everything we've seen so far, okay? Is we have chemical potential energy in the form of gas right here. What's going to happen is this motor converts that chemical potential energy into heat. Heat via the combustion of the gas is combusted and the chemical potential energy releases energy in the form of heat. And then what heat does inside a car engine is it exerts a force on the car pistons, which does work on the car pistons and converts that heat into kinetic energy. And that kinetic energy is what allows our car to move. Okay? Now we have friction between the tires and the ground, or the brakes too, that turns that potential energy or kinetic energy into heat that cannot be used. So friction we can think of as a non-conservative force. We can also think of as what we call like a parasite force if we want to be a little bit informal, in that it siphons off energy that we cannot use. Okay? So let's take a look at the scenarios here. Is it possible to classify each of the following as possible or impossible? Please explain your reasoning. So a roller coaster falls from a height of 20 meters, is able to come a 30-meter hill. A ball is rolling off the floor when it comes to rest. The kinetic energy of the ball is lost in the process. And then C, a car has enough gas to travel 60 miles but manages to travel 70 miles on a horizontal road. Okay? So there is no downhill component or anything like that. So please take a moment to think about these and answer these in your note sheets, and then we'll go over them as a class together. So let's take a look at this first case. A roller coaster falls from a height of 20 meters and is able to overcome a 30-meter hill. All right, so we know if we start out at a height of 20 meters and we're starting from rest, all of our energy is going to be in the form of potential energy. And this potential energy is proportional to our height. So as a result, our object starts off with that amount of potential energy that represents our total mechanical energy. So we can never exceed that total amount of total mechanical energy. So as a result, we can never exceed the 20 meters because that means we'd have more energy available to us than we started out with. And if there's no outside forces doing work or anything like that, adding energy to the system, then that's not possible. We can't exceed the initial amount of energy we have. So as a result, we cannot pass the 30-meter hill because the initial energy of the roller coaster we have, better said, the energy required to overcome a 30-meter hill is greater than the initial amount of energy the roller coaster has. B, a ball is rolling on the floor when it comes to rest. The kinetic energy of the ball is lost in the process. This is possible because the kinetic energy of the ball is not destroyed, but rather converted to heat/thermal energy. Okay? So we can lose the kinetic energy, it just can't be destroyed. The kinetic energy can be converted from one form to another, from kinetic to heat in this case. And then C, a car has enough gas to travel 60 miles, but manages to travel 70 miles. So this is very similar again to the first example, where instead of having our potential energy being proportional to the height, we now have our potential energy being the energy stored in the chemical bonds of the gas, and that's proportional to how far we can travel. So in this case, because our potential energy stored in the gas tank allows us to travel 60 miles, we can never exceed that initial amount of energy we have, so we can never travel 70 miles or beyond 60 miles. So now let's take a look at path independence and conserved energy. Let's tie together some prior concepts that we have seen so far. So 4 identical objects are released from rest at the same height on 4 different frictionless tracks. Which object will reach the ground with the fastest speed? Alright, so take a moment to think about this, answer based on what you think might be happening and based on what we've learned about so far in this unit, and then we'll take a moment to go over discuss what's happening and tie together some loose ends from this unit. So, this one is a tricky question to answer, okay? They're released from frictionless tracks, they're all released from the same height, okay? So first thing to notice, okay, is that since energy is conserved, the total energy remains the same at all points on our tracks, okay? The other thing to take notice is that the path taken for an object to get from one spot to another does not matter. We've talked about path independence before, so the path is not going to matter it takes for our object to fall, okay? So let's take a look what's happening right here. Each object starts from the same height, all right? So as a result, they're all going to start at the same amount of potential energy, okay? As each of these objects fall, okay, each of these objects' potential energy is going to be converted to kinetic energy, regardless of the path taken. Again, the path taken does not matter. So once we reach the bottom right here, all this potential energy for each ball is going to be converted strictly to kinetic energy. Again, we don't have friction here. So as a result, each ball is going to have the same amount of kinetic energy at the bottom of their respective hills. And since kinetic energy is proportional to the motion of our object, that means each ball will be moving with the exact same speed. Now, this might seem weird and counterintuitive because we don't see this in everyday life, but the reason why we don't see this in everyday life is because in everyday life, these ramps actually have friction. And friction will act to slow down each ball depending on the path taken by each ball. So, again, since energy is conserved, or sync, since I apparently forgot how to spell, all have the same kinetic energy at the bottom. So now let's look at how to solve conservation of energy problems. A water bottle rocket is launched with an initial speed of 40 meters per second. What is the maximum height that the rocket will reach? So this is a problem we actually solved back in Unit 2 using kinematics, and we'll actually solve it from the perspective of conservation of energy to show that conservation of energy gives us the same result as kinematics, which is what we should expect. If physics is accurate, then the physics from one unit should match the physics from another unit. So the first thing that we're going to do here is we're going to identify our 2 points of interest, okay? Our first point of interest is the ground. Let's see, where am I at? Is the ground, and our second point of interest is when we reach our maximum height, okay? So now the second thing that we're going to do is we're going to write down what we know about each point of interest. So right here, we know that at the ground, we know our initial velocity is 40 meters per second, and we know that our height on the ground is 0 meters. Now, at our maximum height, we know that our velocity is briefly going to be 0 because we're going to be changing direction, okay? We're going to be changing from going up, which is in the positive direction, our rocket's going up, to now going down, which is going to be in the negative direction. So as a result, okay, to go from positive to negative is going to require a velocity of 0 at our maximum height for a brief moment. So we're going to have a maximum velocity of 0 at our maximum height. And our maximum height is what we are looking for here. So now the third thing that we're going to do is we're going to set the energies of each point equal to each other. So in this case, we're going to have EI equals EF, okay, that is conservation of energy. Our initial total energy equals our final total energy. So we're going to have 1/2 mass times initial velocity squared plus mghi equals 1/2 mass times our final velocity squared plus mghf. This is going to be our initial kinetic plus our initial potential equals our final kinetic plus our final potential, okay? So we can cross out the mghi and the 1/2 mvf squared and make them 0 because in this case, our final velocity is 0, so thus our final kinetic energy is 0, and our initial height is 0, which means our initial potential energy is 0. So anytime a variable is equal to 0, the corresponding type of energy will be equal to 0. So in this case, initial height is 0 implies that my initial potential energy is 0, and my final speed is 0 implies my final kinetic energy is 0. Okay? So now at this point, we're left with 1/2 mvi squared equals mghf. Okay? So what we can take note of here now is, well, what are we going to do with m? We don't have a mass of our water ball rocket. Well, what we can take note of is that there's an m on both sides of this equation, so we can actually cancel out these m's. Oh, that's quite nice. And we can see that mass does not actually have an effect here, which is what we saw back in Unit 2, is that the mass for an object in free fall does not play a role. Okay? So now we can plug in our knowns. 1/2 of 40 squared equals 10 times h. So we're going to get 800 equals 10 times hf, or that our final height is going to be 80 meters. And if you go back all the way to Unit 2, when we did these free fall problems, you'll see that that's the exact same answer as we got using kinematics. And then step 4 is plug in known information. I forgot to bring up step 4, but plug in known information, so this step right here. So now let's take a look at one more practice problem here before we do a check for understanding. So a roller coaster is shown below with an 800 kilogram car initially moving at 10 meters per second on an 80-meter hill. We ask, what is the speed of a roller coaster at the bottom of the hill? So we start off by taking note of where we begin and where we end at, okay? So in this case right here, we begin at the top, okay, where our height is going to be 80 meters, and I have 80 meters per second here, that should just be meters, and then our speed at the top is 10 meters per second, okay? Now at the bottom of the hill right here, our height is going to be 0 meters, and our speed at the bottom of the hill is what we're looking for. So as a result, we start off again, our initial energy is equal to our final energy, so it's going to be our initial kinetic plus our initial potential equals our final kinetic and our final potential. This is never going to change right here, this equation. Now what changes here is the numbers that you're going to be using. So in this case, we can't cross out mghi because our initial height is 80 meters, so we do have some initial potential energy. But we can cross out mghf because our final height is 0, meaning that our final potential energy is 0, okay? So as a result, that's going to leave us with 1/2 mvi squared plus mghi equals 1/2 vf squared. We can see the masses cancel out again, as we would expect now that we saw in the last problem, and we can get 1/2 vi squared plus ghi equals 1/2 vf squared, or 1/2 of 10 squared plus 10 times 80 equals 1/2 of vf squared. So this is going to give us 850 on the left-hand side and 1/2 vf squared on the right-hand side. And so as a result, we're going to have 1700, okay, equals vf squared, and taking the square root of both sides will give us 4.123 meters per second equals our final speed. So that tells us that at the bottom, we'll be moving at a final speed of 41.23 meters per second. Now, the great advantage of conservation of energy is that for this particular problem, we can't apply kinematics because kinematics can only be used for one-dimensional motion, aka we're moving on a straight line. Here we're not moving in a straight line, so we can't use kinematics, but because conservation of energy is path independent, we can use conservation of energy to analyze the motion of this object on the track. Alright, so now let's go ahead and take a look at our last problem right here. A roller coaster is shown below with an 80 kilogram car initially moving at 10 meters per second on an 80-meter hill. So same scenario as before, except now we ask A, what is the height of the loop-de-loop, and B, how fast will the car be moving at the top of the loop-de-loop. So take a moment to work on this, and then we'll bring it back together to discuss how to do this problem right here. Alright, so let's look at how to do this problem right here. Roller coaster activity. Nope, that's not for us. This is just an online lesson. Alright, so for this problem, since the radius... There we go, let's zoom in right here. Alright, so for A, we asked for what the height of loop-de-loop is. So here we just need a little bit of geometry. Our loop-de-loop is a circle, so we can see right here that the height of the circle is going to be the diameter of the circle. So if our radius is 20 meters, that means the diameter is 40 meters. So h equals 40 meters. Alright, so now we ask how fast will the car be moving at the top of the loop-de-loop, okay? So, at the top of the loop-de-loop, alright, or excuse me, at the top of our initial hill, we're moving at 10 meters per second, okay? And our height is 80 meters. On the loop-de-loop now, our initial speed is unknown, and our final height is 40 meters, okay? So we're going to have 1/2 mvi squared plus mghi equals 1/2 mvf squared plus mghf. Again, initial kinetic plus initial potential equals final kinetic plus final potential. We can't cross out any terms here because none of our speeds or heights are equal to 0. So we can't set anything equal to 0. We can still cross out the m's though, which is going to leave us with 1/2 vi squared plus ghi equals 1/2 vf squared plus ghf. So now plugging in our known information, we're going to have 1/2 of 10 squared plus 10 times 80 equals 1/2 vf squared plus 10 times 40, which is going to give us 850 equals 1/2 vf squared plus 400, or 450 equals 1/2 vf squared. Multiplying both sides by 2 gives us 900 equals vf squared, and then taking the square root of both sides gives us 30 meters per second for our speed at the top of the loop-de-loop. And thus, this is how we would solve this example problem right here. And this is our lesson on conservation of energy.